Let me introduce Professor Alan Kay. Professor Alan Kay is best known for his pioneering work on object-oriented programming language and window and graphical user interface design, and for coining the phrase, the best way to predict the future is to invent it. In 2003, Professor Alan Kay received ACM Turing Award. It's considered to be the Nobel Prize of Computing for work on object-oriented programming. Let us welcome Professor Alan Kay.
Thank you. Okay, ground rules here are ask questions whenever you have one, because these classes go quickly. Just think of all the money you're paying for hardly getting anything in an hour. So, programming languages and programming. One of the problems of talking about this in general, especially in one class, is that there have been several thousand programming languages designed and implemented over the years. At any given time, since the early 60s, there have been somewhere between 150 to 200 languages in standard use. And these languages are rather different from each other in certain ways and rather similar to each other in other ways. And so it's very hard to come up with interesting generalizations. And what we're really talking about here is programming. And programming is the simplest thing to describe. It's we do something and the computer does something. And if it does what we wanted it to do, both of us are successful. Programming languages are usually the vehicle for this, and you can think of user interfaces as kind of an impoverished kind of programming language. They used to be richer in that the kinds of things that you did in the user interface were part and parcel of the kinds of programming you could do. And I'm going to show you a few of those things today. So I thought what I'd do is first to just look at a couple of ideas in programming and programming languages and be able to do it so I don't have to explain some programming language you've never seen before. I'm going to take a programming language that is currently in use by about 3 million children called eToys. It's the parent of another widely used programming language for children called Scratch. And some of the same people worked on both of those. And so I'll first take a look at what that experience is like. And so the basic idea in this style of doing programming, it now has a name called live coding. But in fact, live coding goes all the way back to the early 60s. It just never was in the style of the punch card, Unix approach, black screen, VI terminal way of doing things. So the idea is that you just make things in a variety of ways and the computer responds to them. There's no visible compiling or editing. So pick up some paint. One of the things that kids like is to do things that adults do. So you can ask them, why don't you draw a car from a top view, put on some headlights, and we were at Disney for a while, and so the thing we learned at Disney is you must always put on some specular reflections. Like that, and this gives you a graphical object, and it does the kind of things you'd expect with a graphical object. I can give it a name here. I'll call it car. And what's interesting about this object is it has another view. And this is the symbolic view of this object. And so here's a property of it called the heading of it. It says the heading is 0, and if I rotate the car, you can see it's showing me the degrees from north, minus and plus, and this is interface is reflexive, so if I go in here and right, so everything is bi-connected here, and also here's a behavior of the car, turn by 5. If I click it, it turns the car. If I drag it out, it makes me a little script. If I get the script is now just infinitely looping. And if I pull out another thing, now each time I'm doing this, there's a compilation going on, but it's sub-second. So it's actually compiling code underneath it. And I can actually even drive my little car. So 0 makes it go straight. But in fact, it's hard to drive the car this way. And it's a little bit like kissing your sister. So you really want to have a steering wheel. So we'll just make a steering wheel. And we'll call it wheel. And again, if we look inside here, we see, oh, this is just the same kind of object. It's just got a different costume on it. And again, it has a heading, and I get the same behavior from it. But notice that we got the car to turn by changing this number here, and that's kind of an imitation of picking up this value and dropping it into the script. And now we get to do this. So you're just starting out here, but let me tell you, if you program in a language here at UCLA that doesn't allow you to do this little demo right off the bat, something is wrong, because we're looking at something that goes back 40 years. This is just because you don't know what you're getting into here. I'm just trying to show you that there doesn't have to be a compile phase. There doesn't have to be edits of files. It can all be done lickety-split. Okay, so I've got a little car there, and the other thing I can do is make lots of them. So now I'm going to play a game. Got a red car and a blue car, and I'm going to make them small. Can you see them? Blue guy and the red guy there. And the two programs I'm going to run here, this little kid system has automatic multitasking, as many tasks as you want. So I'm going to say go forward by 1 and turn randomly. And this one says do this guy, and if a blue guy touches a red guy, then make the blue guy red. So this is like an infection programming. And so if I say go, at the top here I'm plotting the infected against the non-infected. You can see that the big open space here that the village is kind of like a long time constant. The probability that the two guys are going to hit is fairly low, so I'm going to get that behavior. But what about 1,000? And all of a sudden I get that. So there's another thing. If your programming language doesn't allow you to make objects by the hundreds of thousands and run them in parallel, then you have to worry about what kind of language you're programming in. So the kids with this little program that they wrote, there's no mystery here. They wrote this program. So now they can explore by saying, well, okay, how about 200? And again, the sparseness acts like a longer time constant between infections, but eventually they all die. And we get this longer thing, so the kids will say, okay, well, how about 80? Okay, now they're starting to root for the ones that are maybe, nope. So this is kind of an experiment in system dynamics for 10-year-olds. And it's something that many parts of the world don't actually understand on any terms. Because this first curve that I showed, the one that went up rapidly, is like typhoid. And so if this last one was a disease, what would it be like? What disease would it be? Blurt it out. Let's see, it's a disease that's already killed 100 million people. Yeah, come on. Remember, you're at UCLA now. Yeah. So why does it kill that many people when typhoid is much more virulent? And the answer is, unless you know that a contagious, incurable, deadly disease is always going to kill everybody off, no matter what the time constant is, you're not going to do anything when it doesn't look like anything's going on. Remember, people are also being born. So for a while, when AIDS is doing its work, the population is actually still rising. And if you don't happen to know this feature of system dynamics, you might just ignore it or say it's just for minorities or something like that. Then all of a sudden, you've got a majority of your population infected. Okay, so that's a little thought experiment that children can do. It's important because if you think about what is it that we need to know today, it's not so much knowing that 2 + 2 = 4 or how to compute a tip for a waiter. It actually has to do with systems dynamics because the world, particularly biologically, is more connected in more ways than it ever has been before. And also our people in Congress in Washington could do well to do a few of these experiments because they'd actually have some sense of how unstable systems are, and you shouldn't monkey with them. Okay, so back here we'll turn this guy off, and I'm going to do 2 other quick little experiments here. First one is to make a little robot car now that we made one that can be driven, and for that I will need a track. So I'll get sort of a brown track here. And robots need sensors, so I need to put a sensor on this guy. So I'll just draw one in here. Like this. We'll use this to track where we actually are. And now we need to make a program. And we can think out this program first. So one of the things we do with children is get them to go around the wall of their classroom with their eyes closed. And the way to do that, they soon find out, is you go until you hit the wall and then you turn away. But as soon as you lose the wall, you have to go back into it. You keep on going. If you don't do that right away, you may lose where the wall actually is. So to write that little program, we want the car is always going to go forward, so I can get that. We're going to test whether we're touching the wall or not. Here's a test that will test, let's see, how about the car's blue color sees the wall's brown color. And then we have to figure out which way to turn here. Okay, I'm going to put in 2 turns by 5s, but let's think it through. So if we don't have the wall here, which way do we want to turn? 5 or minus 5? 5. Okay. So that's no, and so for yes, we'll just take a guess and try minus 5 here. And we'll just start it going. Okay, who can see what the flaw with this program is? Somebody tell me. Well, don't worry about efficiency. Humans aren't efficient, but we're smart. What's the condition under which it can lose this wall? It's going to do it this time. But if I made a sharp turn, right, it's got a fixed radius to get back. So probably when I lose the wall, I might even want to stop the car, slow it way, way down to give me a real chance of contacting the wall again. Okay, so that's a little experiment in making a feedback thing. Now what I want to do is to turn this thing into a wriggly worm. And to do that, I want to make a script that is going to change its shape. So here's my little thing that says car look like something. But I don't have anything to make it look like. So I will... Somebody talking? Now somebody isn't talking. Okay. So now I'm going to draw a couple of pictures for the wriggly worm part of this. I'll make a blue top and maybe a brown bottom here. And just to test this out, this one is called Sketch 1, so if I say do it, okay, so that worked. But I need another one in order to make it wriggle. So I will make a twin to it right here. But with a wriggle the other way. Okay, now I need to move back and forth between each one of these, and to choose which one of these, I'm going to need something that we might call a little data structure here. I'm going to put the worms in it. Now I'm going to look, again, see all of the objects here have the same kind of user interface. I'm going to look down here and see, oh yeah, here's the cursor. Here's one that says the holders player at the cursor. So I'm going to put that in there. And here's the cursor control. So I'm going to toss that in there. I'm going to say what I want to do is just increase the cursor over and over again. And so now I'll start this script up. And you see what it's doing here. Okay? Now we could have put that in as a feature for the children. But then the children wouldn't understand how to do animation. So when you're trying to teach somebody something, you don't want too many features. You want them to actually do the programming themselves. And meanwhile, the children have forgotten about these other scripts that are there. So I could turn on this one and drive the little worm around. Or what about this one? Okay, so that's kind of simple programming. And the other thing that you want to be able to get a handle on pretty early in your programming career is metaprogramming. And metaprogramming in this case means I want to make another language other than eToys. And I'm going to do it for the particle system kinds of stuff. So these are now eToy objects in there. These are the scripts for the whole interpreter. I'm going to use the animate. Remember the animation thing? So if you know a little bit about program counters, the animation system is rather like running a program counter along. When you're doing animations, what you're doing is saying display the guy that's there. In this case, we're going to execute instructions. And so I'm actually going to turn on the eval here. You can see it maybe a little quivering a little bit here. It's dying for some input. And then the instructions are going to be implemented using these scripts, which I've already written. And now I just have to build the instruction. And so this one is a test that says if you can move, this one says then move. Okay, so now it's executing that instruction. And this one says if a blue guy hits a red guy, then make them both red. Let's see if we're lucky here. Yep. Okay? So programming, and again, when you're taking that Java class and you spent the first couple of weeks not really writing a program yet, think about what it's like to write another programming language in Java. Should be really easy, but it isn't. Okay, so one of the theories about designing programming languages is because children are part of our world and children grow up into being us, we should be able to have them be able to start learning how to program just as we're learning how to program. And then if you do that well, the stuff that children find easy and powerful are actually clues for how to design a programming language yourself. Okay, and so what we've been looking at here is, here's computer memory, and down a fly speck in the machine is actually some logic gates on a chip, one corner of a chip, and around it is nanocode, microcode on the chip itself. And that might be an 86 architecture kind of chip. But most of the chips are done the same way. There's some simple logic, like this is the arithmetic, these are registers, the arithmetic unit, and so forth. And then it's made into a slightly more complicated processor by putting a lowest level of programming there in pretty elemental terms. And it's not always easy to write these low-level programs. And then nobody wants to program in that. So in this case, what we're looking at is a virtual machine coded ultimately in these terms that makes the computer look like a Smalltalk machine. And at this level, there's an area on there that's manifested where the display is going to go. And then in that, we write a development system, which you still haven't seen. Yes?
You haven't introduced what Smalltalk is.
I'm not going to. But thank you for the thought. Yeah, it's too complicated. Smalltalk is a programming language. That's all we need to know. It has a development system that's written in itself. And the eToys system that you saw, which is putting up this slide, here is written in Smalltalk. And then I just made a little interpreter in the eToys machine for doing the rule-based particle system stuff. And this is a very typical way of going about handling problems. It's not the only way. Some people like to program down here and write tons of programs to deal with the very same problems. Another way of doing it is find languages that fit the problems gracefully, and then the amount of code you have to write to get to the next level is not that large. And all of this is kind of an example of Turing's idea of being able to simulate any kind of mechanism on a relatively simple mechanism that has a few pieces of logic and a fair amount of memory. Okay, so that's the kiddie world. Now let's take a look at the adult world, where we're going to go from programs that have tens of lines in the kiddie world but can still do interesting things to adult programs which tend to have zillions of lines and are surprisingly weak. And in order to come up with a metric for this, I'm going to use a metric of lines of code. It's not the only metric you could use, but a line of code is something that a programmer has to write. So it is one kind of unit of work, and it's also a unit of space. So a 400-page book has 20,000 lines. Could be English, but it could be code. Could be in machine code, it could be in C, it could be in Java. And a foot of books is about 300,000 lines, and a meter of books stacked up like this is 1,000,000 lines, so that's a good metric. 1,000,000 lines of code per meter and stacked up books. And the Empire State Building is 22,000 books high and 440 million lines of code. Right? So if you've ever heard, anybody heard of any programming systems that have 400 million lines of code? Yes, no? Come on. Yeah. Yeah. Take a look at our government sometime. In fact, if you look at your own little laptop, if you happen to be running Microsoft, the operating system is about 120 million lines of code. Remember, it's just the operating system. It hasn't done anything for you yet. It's just sitting there. And then Microsoft Office is over 100 million lines of code. So that's 220 million lines of code. It's about 11,000 books of code. Anybody ever read all that code? No way. Very few people who read it all have read 11,000 books of anything. I can guarantee you, if you read it all, you're not going to read 11,000 books of code. So most of the code has never been overviewed by any single person or even any single group. In fact, much of the code in there is code that isn't even run, but they're afraid to take it out because they don't know whether it's run or not. And this is a problem. On the other hand, looking at it from the standpoint of writing code, when you look at the actual features you get for this 220 million lines of code, it doesn't seem like it should take 220 million lines of code. It just shouldn't. In fact, the first time around it was done at Xerox PARC, did about half of this, and it only took 10,000 lines of code. So something happened. Some kind of explosion of complications and complexity. And here, just to make you feel better, I located a large financial products company whose name I will not put here that has more than 400 million lines of code in its primary offerings to its customers. So this is what they are actually maintaining, and you can tell they're a little old-fashioned because their user interface is given in terms of screens, which harks back to the days of mainframes. they have 170,000 screens they have to deal with, and that's about 20,000 books, or almost an Empire State Building worth of code. However, if you're looking for a job, if you came to UCLA to learn to program and get a job, it's just this kind of stuff that you actually have to learn about, because that is what business is mired in right now. This is what they're hiring people. This is why they're crying for programmers. Not to do better, but just to take care of the mess that is already there. Think about that. Okay. So I'm going to I'll show you a couple of examples in the time that's left of what might be done about this part of personal computing, these several hundred millions of lines of code. Okay, so let's take a look at this problem from a slightly different perspective. Over here we've got some gates. Over here we've got a problem. This is what we need. We need to do something over here, and the question is what is it going to take us to get from there to there these days? And so in terms of machine code, lots of the kinds of things I'm talking about are literally billions of lines of code, because machine code is written one instruction per line of code. And maybe C gives 8 to 10 machine code instructions per line of code, so maybe something that would be billions would be hundreds of millions in C. And we can imagine a higher level language than C. Not that Java is that much higher level than C, but you can imagine something higher level. You can imagine something higher level. You can imagine something that might do a lot of these tasks in just thousands of lines of code. And the question is, why do we stay here down at the gear level for most of the programming that is still done today? And there's not a lot of the organization of code at this level, which is a little bit more like the way biology organizes itself. So almost none of this still being done. Okay, so the programming effort comes down as we go to higher and higher level languages. But computer science has not actually been up to the challenge of putting in the amount of invention that's necessary to make programming systems that do this amount of work for us. So we can think of an in-between is just a lot of work for any kind of programming language you do, because there's packaging, there's documentation, there's debuggers, there's an enormous amount of work that has to be done. And the idea is that with more work, which gets tougher as you come this way, you actually reduce the general programming effort. So this is not popular. So virtually all of the programming in business in the US today is done at this level still. And this is a level that is really not different from the level of programming in the 60s. Almost nothing has changed. New languages have come along, but they have not upped their level in any significant way. But just to go against the tide here, even though you're going to be studying a lot of this stuff here, I just want to make you aware of these ideas down here, which if you're interested in research and in making things better, you might poke your head into. Now, what's funny about history is that there are people who are absolute geniuses who transcend the time in which they live. So 50 years ago, there was no computer graphics. This is the guy who invented computer graphics, and he also invented object-oriented design systems. So he actually did the work in 62 and wrote it up in 63, so this is still the 50th anniversary of this. And I thought you'd like to see what this very first interactive graphics system looked like and what it could do. Now, the first thing you have to visualize is this guy is sitting here with a pointer in his hand, a light pen, but he's in a computer that is about 8 times, maybe 10 times the size of this room. It was close to the size of at least the first Franz Hall building. It had its own roof. It was the building. And it was an air defense computer, and from 3 o'clock in the morning to 6 o'clock in the morning, they let this one guy play around with it. And so here's what he did. And by the way, this is not actually a computer display. It just was an oscilloscope that put up spots. So the first thing he had to do was to write programs that would make lines and arcs and so forth. And about a third of the capacity of this enormous machine was used just to make a simulated graphics display because there were no graphics displays. Okay, so this will give you an idea. So he gets some ink. And he just sketches in this flange because, look, he's pointing at it now, and he's giving it a constraint to make everybody mutually perpendicular. And what you saw there was Sketchpad solving the problem for him. Right? So the way you programmed this system was by telling it what you wanted to have true, and Sketchpad would figure out how to have it be true. Same idea here, make these two guys parallel. Now the constraint is collinearity. Put these lines down, these dashes I'm putting in here, down on top of the guidelines. Now he says, okay, let's make the guidelines transparent, and now we've got a hole in the flange. And you notice it has continuous zooming, the first clipping window ever done. It was actually, the drawing is done on a sheet of virtual paper about 1/3 of a mile square. Now he wants to make a rivet. He's going to use the center here for the arc. And now he's going to do the same trick. He's going to say to these guys, take these guys and make them all mutually perpendicular. That's going to drag the cross pieces. It's going to drag the top of the rivet. Now he's going to show, I'll start off with different initial starting conditions, and I'll still get something that obeys the constraints that I gave it. Now, he could have put in absolute numbers in there. He could have put in ratios. This is why it's called Sketchpad. The idea is you should be able to work quickly, get a rough idea of it, and then tell the computer the rules that if they were solved would complete it. Okay, now he's showing that what he drew is not just a rivet, but it's what we call a class in an object-oriented language, which he called a master. So what he drew there was the master drawing of a rivet, and what he's manipulating here is an instance of the rivet. So now he's showing, yeah, I can make more instances of the rivet, and I can make them different sizes and so forth. But he forgot that cross piece, so he goes to the master, makes those guys transparent, and we can see the rivet feels, the instances of the rivet feels those things. Then the last part of this demo is that he can take anything that he's constructed and make it into a master. So now this is a master drawing of a flange with a rivet in it. And now he's making instances of those. Okay? So this is a, yes? Go ahead.
So the rivet and the rectangular thing, they're based on different parts of the same distribution. When it switches from the rivet image to the rectangular thing, they're just different parts of the same sheet, right?
Yeah. Yeah, in fact, on the larger movie, which you can find online, you can see the sheet is populated with lots of different things on it. Yes? Oh, okay. Okay, so you have to realize this was a PhD thesis. This was done in 1 year by one person. And what the contributions were is first interactive computer graphics, object-oriented design structures, constraints for programming, so you didn't program it using sequential code at all. And one of the great final things he did was to show how you could make a bridge simulation without Sketchpad knowing about bridges ahead of time. Because the whole point of this thing was that Sketchpad was not supposed to know ahead of time what you were going to try and do in it. The idea is you should be able to do everything. And in fact, all of these drawings were made by Sketchpad, and the text here, each text figure is actually a drawing in Sketchpad. So there's a master for F, and everywhere there's an F, there's an instance of it. So the whole system was done in this thing. And I once asked Ivan, how could you have done computer graphics, object-oriented design, and constraint-based programming all by yourself in 1 year? And he said, well, I didn't know it was hard. Since then, okay, so the bridge, there's no movie of the bridge because it took the supercomputer back in 1962 about 20 seconds for each time step on it, because the computer power of this computer the size of a building was about that of a greeting card today. But to celebrate the anniversary of this system, a couple of the guys at Viewpoints, Bert Freudenberg and Yoshiki Oshima, made a version of this bridge. A sketch, and we put in the twinkling there, so it would look like the display back then. And so you can move things in. You can turn on gravity. You can hang a weight from it. And even when it settles down, it hasn't really settled down. If I turn on the decimal points here, see, it's still wiggling, just like real bridges do. And it's interesting to watch what happens when I stick this beam in here. Take a look at the numbers of the stress and strain around it when I drop this guy in here. And notice this guy over on the left felt that ripple across. Yeah, so one of the main things that's got people going from Sketchpad, most of it was too hard for people to really know what to do with, but one thing they were sure about was they needed better looking displays. So here's the very same thing rendered with a modern display, and we can do a few more tricks, like we can give letters weight. Okay, and we programmed this a little bit differently than, in fact, we've done this several times now. One of the students in this class last year, Matthew Goldberg, did an internship with us, and did a different version of this. Did a nice job of it. We programmed it up in terms of 3 constraints. Not the same kind of constraints that Ivan used, but a different kind of constraint. For instance, this one looks suspiciously like it might have something to do with gravity. So this is, way to think of it is this is the 3-line program here. So if I turn this off, so all we've got left is the spring tension here. It should all null out, which it does. So we'll turn gravity back on again. And this bottom guy is the constraint for these pins. So this bridge is pinned together, and if I turn off the pin constraint that's holding everything together in this simulation, yeah, so remember all those costumes? That's all that bridge was. And we can repurpose those costumes into something else, like the user interface of this system. I'm giving the, right, so this is a system that we programmed ourselves at Viewpoints. And it's a system I'm giving this talk in. I'm not, obviously not using PowerPoint, because you can't program in PowerPoint. And I'm using it to show you, I'm going to show you one example because that's all I have time for. And that is how the graphics in this system were programmed. Now, usually the graphics in your personal computer are about 500,000 to 1 million lines of code to do all of the compositing and so forth. And what we're going to look at here is just take a look at the rendering part of this, of being able to paint a pixel with the right shade. So Dan Emelang here is a graduate student at UC San Diego who works with us, came up with this formula. So it's a nice little piece of math to represent it. Here's a programming language that is as close to the formula as possible. It's about twice the size of the math, but it actually runs, and it handles all rendering stuff done like this. And I'll, just to give you now we have this flow of stuff that this programming graphics language sets up, and what we wind up getting is something that's very complex to look at and debug. But Brett Victor, look him up on Google, did this visualizer that's created automatically from the code I just showed you. And this is a live system. So here's I'm going to turn a D into a B here. And if I want to know where this pixel in the rendering comes from, I can just put the mouse on it and touches this. If I want to see where this guy is handled in the code, if I want to see how the pipeline that's set up here of these 5 small programs is here, I can just go here. If I want to, where did this pixel come from? What happens if I turn this? So when you're doing languages of the future, the system is going to have to also produce the debuggers along with the languages themselves. Okay, I think it's a hard stop at 10 of, so I won't put any strain on you. But if you're interested, hang around and ask some questions. And with that, thank you very much.